Hi everybody, welcome to my video, Mid-Ocean Spreading Ridges, Turning Earth Inside Out. The picture you're looking at is a hydrothermal vent on the ocean floor where a mid-ocean ridge is discharging hot gases and elements and a whole lot of heat into the ocean. Mid-ocean ridges represent a link between the deep mantle of Earth and its surface, where the Earth can effectively pass heat and material outward to the surface. Mid-ocean ridges were discovered by geophysicists in the 1950s and 60s who were surveying the bathymetry of the ocean floor. What they saw was startling. Huge mountain ranges running up and down the center of many of our ocean basins. For example, the North Atlantic Ocean, separating the eastern U.S. from Africa. These mountain ranges were eventually recognized as mid-ocean spreading ridges, a very important type of divergent plate boundary that exists all around the world. And they're shown here in this map as these red lines, for example, separating the African plate from the South American plate and the South American plate from the Pacific plate. In essence, these act like seams or stitching on a baseball, holding together this network of tectonic plates that covers Earth's surface. But unlike a baseball, this is not a fixed or constant or stable system. And this video helps to illustrate that point. Mid-ocean ridges are places where mantle material upwells as part of a convection cell. So the mantle is constantly circulating by convection, and mid-ocean ridges are where that material upwells to the surface. It melts and it cools as new ocean crust. And that new ocean crust essentially acts to resurface the Earth. It's literally creating new material to cover Earth. But we know that the size of Earth is not changing. The surface area is constant. So for every meter squared of new oceanic crust that's created at a spreading ridge, an equal amount of area must be destroyed where oceanic lithosphere is subducted down a subduction zone. A great example here is subduction beneath the western side of South America, while an equal amount of material, or let's call it almost equal amount of material, is created in the Atlantic Ocean. So these tectonic processes are constantly resurfacing Earth. From a research perspective, this raises a lot of interesting questions. Because mid-ocean ridges provide a link between mantle convection and plate tectonics, if we can understand how mid-ocean ridges work, it might tell us something about what actually drives plate tectonics and the relationship between convection and tectonics. So a couple of big questions. What causes mantle material to upwell at mid-ocean ridges? Is it actively bubbling to the surface, or is it being passively drawn to the surface? And how does that process of upwelling cause plates to spread apart? Is it related or is it not related? What's actually forcing those plates to spread apart at a mid-ocean ridge? And from the answer of these two questions may well arise this question of how exactly does plate tectonics arise from mantle convection? Are the rigid plates actually driving convection by essentially sinking back into the mantle? Or is it mantle convection that's simply circulating and percolating away, and the plates are really just along for the ride as part of that convective cycling? So these are some of the big questions of plate tectonics, and mid-ocean ridges are really a good starting point to explore them. So in this video, I want to cover three topics. First, I want to talk about what do we know about oceanic crust? What can we observe both from looking at rocks on the surface and from seismic imaging? Then I want to go from there to what are the processes that form oceanic crust and lithosphere? We'll look at decompression melting and lithospheric accretion, or underplating. And then I'll finish by revisiting some models for seafloor spreading in thinking about what might actually drive mid-ocean ridge spreading. So I want to start by taking you to Oman, where nearly the entire country of Oman is covered with what's called an ophiolite. An ophiolite is essentially a slice of oceanic lithosphere that was thrust up from the base of the ocean and onto the surface where it is exposed today. So if you look at this geologic map of Oman, all the blues are gabbros, which represent cooled magma at the base of an oceanic crust, and all the greens are peridotite, which represent lithospheric mantle that was actually accreted onto the base of the oceanic crust. So if we look at these peridotites in Oman or elsewhere, we can actually start to understand how oceanic lithosphere forms. And here's a simplified diagram of an ophiolite, okay? At the top of an ophiolite is pillow basalts. These are lava flows that are erupted underwater. And because they're erupted underwater, they quench and cool almost immediately into these system of tubes, essentially, or pillows, where the outside of the tube or the pillow is a glassy basalt that cooled immediately, and the inside is a more typical basalt that may have continued to flow and cool slowly. So the result is this kind of series of snake-like pillows where these little tubes were being kind of pulsed out onto the surface of the ocean floor and cooling pretty quickly. So these pillow basalts are fed by what are called sheeted dikes or basalt dikes. These are essentially vertical conduits that were acting as periodically as pipes to pump hot basalt magma from a magma chamber up into these pillow basalts sitting above. These sheeted dikes were fed, as I said, by a magma chamber. And when that magma chamber cooled, it becomes a rock called gabbro. Often gabbro will have a coarse crystalline texture of plagioclase and pyroxene crystals. And these large crystals show that it cooled slowly at the base of the oceanic crust. Now, below the gabbro is what's called the moho. We've learned about this before. The moho is the base of the crust. And as you pass through the moho, you pass into peridotite rock. This is the mantle, okay? And specifically, this is lithospheric mantle that was underplated onto the crust. And a true petrologist would call this depleted peridotite because it was melting of this peridotite that fed the gabbro magma chamber, okay? And so it has a certain chemical composition that is depleted. So the observations we can make from an ophiolite are directly supported by seismic tomography, which we've also talked about in previous lectures. And what seismic tomography shows, for example, this cross-section of seismic velocities across the East Pacific spreading ridge, what this shows is that, for one, oceanic crust has a roughly constant thickness of about 8 to 10 kilometers wherever you see it. And what that means is that essentially the processes and perhaps the rate of magma supply that form oceanic crust are essentially constant over time. There's not a big variation in that thickness. And specifically, if you image across an active spreading ridge, what you see are indeed the layer of extrusive pillow basalts, the layer of sheeted dikes, and sitting below the sheeted dikes is a lens of magma with very low seismic velocities. And those are typically 1 to 2 kilometers wide, maybe 100 kilometers thick, and they're discontinuous. They don't exist everywhere. The amount of available magma varies as you go along the axis of the spreading ridge. And keep in mind, when this magma cools, these chambers cool, they're going to eventually solidify into that thick gabbro layer that makes up the lower part of oceanic crust. So now that we know something about what the oceanic crust looks like, let's look at the processes that actually form this. And I would be remiss not to tell you a little bit about decompression partial melting. This is how the melts are actually generated as the mantle rises beneath a spreading ridge. And essentially what happens is illustrated by this figure, which shows depth or pressure on the y-axis and temperature along the x-axis. So this red line shows the typical change in temperature with depth, the geothermal gradient. This purple line shows the melting point of mantle peridotite. And notice that that isn't constant. That melting point increases with depth because pressure is getting higher as you go deeper. Or conversely, you can think of that melting point as getting lower as we come towards the surface and pressure drops. So if a peridotite comes to the surface slowly, it would follow this geothermal gradient, and it would never actually get hot enough at a given pressure to actually cross this melting line. But at mid-ocean ridges, what happens is that the peridotite is coming up so quickly that essentially it follows this trajectory where the pressure drops really quickly and the temperature essentially stays the same or doesn't drop much. And that allows the peridotite rock to cross this melting line and begin to melt. That triggers partial melting, and that is how we're going to generate ocean crust at a spreading ridge. One interesting note is that this partial melting is essentially a feedback. As melting occurs and liquid starts to accumulate, it essentially reduces the density of the rock, which creates even more buoyancy and causes the rock to rise upwards even faster, triggering more melting. So that's how we generate melts at a spreading ridge, and that's how we generate oceanic crust. But we know that crust is only 10 kilometers thick, and a full section of oceanic lithosphere is much thicker. And that thickening of the lithosphere happens as the crust moves away from the spreading ridge over time. We know that that crust moves laterally away as new material is created, such that the age of oceanic lithosphere is essentially 0 at the spreading ridge, and it might be much older, say 100 million years, off far from the ridge. As the lithosphere moves away, it's cooling. And as it's cooling, that wave of cooling essentially extends into the asthenosphere, and we start to essentially cool asthenosphere and underplate it or accrete it as mantle lithosphere. Essentially, we convert from a hot asthenosphere to a cold, rigid mantle lithosphere. And we underplate slowly over time, causing the lithosphere to thicken. As it becomes thicker, it actually becomes denser. And eventually, that thick, dense oceanic lithosphere may become so dense that it will actually subduct back into the mantle. And that may be a major driving force in plate tectonics. So in summary, we've looked at ophiolites, we've looked at seismic data, we've talked about the processes of decompression, melting, and underplating. Let's bring this all together. Essentially, what happens at mid-ocean ridges? Mantle material rises, it partially melts, it creates magma. That magma feeds dikes and cools as gabbro to create oceanic crust that's roughly 8 to 10 kilometers thick. As that crust moves away from the ridge, we thicken the lithosphere by underplating new lithospheric mantle. So now that you know how oceanic lithosphere is created, let's circle back to our original questions. What drives seafloor spreading? And I want to look at 3 different models. And all these models are essentially predicated on the idea that mantle upwelling is co-located with seafloor spreading, okay? But the question is, why is this mantle upwelling at mid-ocean ridges. And the first model, the buoyant upwelling model, essentially proposes that mantle material is rising because it's already buoyant. It has a low density because it's warm or because it has some liquid in it, or maybe both. And as that buoyant material rises, it creates lateral forces, what someone might call ridge push, that push the plates away and drive spreading. Most people don't believe this model. However, it must play some role, and we know that it plays some role largely by looking at rift zones. Rift zones are essentially incipient spreading ridges. They're the very early stages of oceanic spreading. And the best example is the East African Rift here in East Africa, where the African continent is essentially being split by a rift down the middle. There's extensional stresses across it, and eventually this is going to become a spreading ridge in a new ocean basin will develop here. But what we see is that that's not happening by chance. The reason rifting is initiating here is because there's a thermally buoyant plume that's actually rising up beneath East Africa, causing higher elevations and contributing to extensional stresses. So in this case, we know that a plume of mantle is already buoyant, and it is actually causing extensional stresses in East Africa. Now, in contrast is the passive upwelling model. This is the idea that mid-ocean ridges aren't fed by a naturally buoyant plume, but that instead mantle material rises to fill an empty space, and that essentially the plates on either side of the ridge are already being pulled apart, and they're creating an empty space or a vacuum that's basically drawing mantle material upwards to fill that space. One implication of this passive upwelling model is that a major forcing would be slab pull, because in this model we need something to actually be pulling apart the ridge. And in this model, that thing might be the force of subducting oceanic lithosphere as it essentially sinks back into the mantle under its own weight. And that could actually exert a force across the lithosphere and pull spreading ridges apart. One piece of evidence for this is that if you look at earthquakes at mid-ocean spreading ridges, which reflect faulting, they show that most faulting at earthquakes is actually extensional faulting. Literally, the crust is being pulled apart in response to some stretching force. Which would be the opposite of ridge push, which would generate thrust or compressional earthquakes. So a third model that may also play a role is called basal traction. And this is the idea that as the mantle convects beneath the lithosphere, it's essentially exerting a traction, something like a conveyor belt, that's pulling the plates along above it, kind of like an escalator, where the plate would be a human riding on the escalator. This model isn't favored, but it has gained some support recently. A recent paper in particular showed something quite interesting, that spreading ridges are not always spreading in the direction of mantle flow. This recent study essentially showed that there's a difference between the direction of spreading, shown by these white arrows, and the direction of divergent mantle flow beneath the ridge. And they essentially argue that the direction of mantle flow has recently changed direction, and that the spreading ridge simply hasn't caught up with that yet. So in summary, we set out to figure out how mid-ocean ridges work and maybe use that to understand the relationship between mantle convection and plate tectonics. We started with some observations. We showed that ophiolites are made of pillow basalts fed by dikes, all derived from a magma chamber that cools to a gabbro. That's confirmed by seismic imaging, which shows that ocean crust is roughly a constant thickness and that there's actually magma chambers sitting below active spreading ridges. We then talked about some processes that might feed this spreading ridges. For example, decompression, partial melting, that generates magma beneath a spreading ridge. And we also talked about how oceanic lithosphere thickens away from the spreading ridge by a process called accretion or underplating of mantle lithosphere, and that eventually leads to thick, dense, old oceanic lithosphere. And we finished by talking actually about 3 models, which was the buoyancy model, the passive upwelling model, and the basal traction model. Thanks for listening, and here's a few concept questions.